My pleasure to introduce Dr. Vinesh Vishnu, an accomplished mechanical engineer and researcher with over 8 years of experience in teaching and research. He specializes in wear and corrosion behavior of additively manufactured alloys and post-treatment techniques like laser shock peening and heat treatment. Dr. Vinesh is a proud alumnus of NIT Calicut, where he earned his PhD in mechanical engineering, focusing on tribological performance and material characterization. He has published extensively in high impact SCI journals and collaborated with leading institutions like RRCAT and ISRO. We are honored to have him here today to share his expertise. Please join me in welcoming Dr. Vinesh Vishnu.
Thank you, Vishnu, for the nice introduction. First of all, I would like to thank Dr. Basil sir for inviting me to conduct this session. My research area is mainly the effect of post-treatments on wear and corrosion of additively manufactured components. And laser shock peening is one of the surface treatment technique that we can adopt in order to improve the surface qualities as well as the mechanical properties of the mechanical components, especially the metal parts. So today I'm going to discuss about the laser shock peening and its effects on metal parts. It's an overview of especially aluminum as well as stainless steel materials, which are the key materials nowadays used in aerospace, automotive as well as bioimplants. So I'm going to cover the main aspects of laser shock peening on aluminum as well as stainless steel materials. Moving on to the slide. So in this slide, I just briefly introduce the laser shock peening process in detail, then the different techniques and different methods that we are going to follow in laser shock peening process depending upon the materials. Then the enhanced properties with respect to the laser shock peening operation. Then the application of the laser shock peening with respect to the certain condition. Then the references. So this is the outline of the presentation. Moving on to the laser shock peening operation. The term itself, it is known as laser shock peening. So we can divide the term into three: laser, shock, and peening. Laser, we know that laser is a energy source that we are going to use to peen the surface or to treat the surface. As I told you before, laser shock peening is a kind of surface treatment we are using to improve the surface qualities as well as the mechanical properties of the metal components. So the second term is shock. Shock is nothing but whenever we are using a laser or when laser is allowed to incident on metal surfaces, when it is in contact with the metal surface, it develops a shock wave through the material, and as a result, it enhances the surface qualities as well as the mechanical properties of the component. That is why the term is called shock peening. So the figure shows that. So in the case we have a target material or the material which we are using for enhanced properties. So on the material we are going to peen or we are going to incident the laser. Here the condition is that the laser what we are going to use is a pulsed laser. Pulsed laser means a laser is not in continuous form. Normally we see that the laser will be in a continuous fashion. Clear? But a pulsed laser means a laser will be varying its energy with respect to the time. That means the laser energy is it distributes with respect to the given time. That is known as pulsed laser. Okay, so here we use a pulsed laser beam, and when it is allowed to incident on the metal surface, what actually happens is it creates a plasma. Okay, that plasma which produced by means of laser peening operation, which induces a high pressure shock wave. When the shock wave is transmitted through the metal surface, it induces high residual stresses or high compressive residual stresses inside the material. And this high compressive residual stress, which imparts better surface qualities as well as the properties of the component or the part which we are going to use. So here you can see that this is your metal part. So over the metal part, we just protect the surface of the metal part by means of a protective film. It is known as ablative layer. It can be either a carbon type or a glass material, or you can use black paint also. It's used to prevent the material from the thermal shock. When laser hits on the surface, we know that it is going to interact with the metal surface and it creates a high thermal shock wave. So in order to avoid the direct interaction with the metal, we use this type of ablative layer. Then, and we can see a confining layer. Confining layer is nothing but a water layer we use, continuous water supply we use to provide confinement of the plasma. So whenever the laser is going to incident on the surface of the material, it is going to develop a plasma. So in order to confine the plasma to the metal surface, we know that whenever there is a heat flow, it may travel or it may vary the distribution of heat along the direction of flow. So in order to confine, in order to get the maximum effect on the metal surface, or in order to confine it onto the surface of the metal, we use a confining layer. So we can use three types of confining layer, but here we use water as the confining layer. So which helps the plasma to focus on the metal surface and produce high shock wave on the surface of the material. So that is the working principle of this laser shock peening technique. Then when the plasma is generated or when it is confined to the material surface, it develops a shock wave and it is known as plasma pressure. Clear? That plasma pressure is going to develop a high pressure shock wave. That shock wave, when transfer or when it transmits through the metal surface or the layer of your material, it is going to develop compressive resonances. Clear? So with respect to the peened surface, so we are going to peen or we are going to incident the laser over the top surface of the material. Clear? And with respect to the thickness of the material, with respect to the layer thickness, it is going to affect or it is going to impart residue stresses or compressive stresses over the metal surface. So that is the working principle in the process. So laser shock peening, as we know, it is an advanced surface treatment technology. It is used to improve the mechanical performance of the mechanical or metallic parts by inducing beneficial compressive residue stresses. Okay, and before going into the deep, you must know what is the significance of tensile residue stress and compressive stresses over the surface of the material. Clear? Now, for example, if you want to cut a sheet or if you want to cut a plain sheet or if you want to cut a wooden piece, or simply you can consider, since all of you are from, I think most of you are from Kerala, if you want to cut halwa, how do you keep it? If you keep it very closed or if you apply force from the either side of the halwa, then it will become very rigid, isn't so? So when you start cutting, then it will be easy for you to cut it. When you stretch it, it will be easy. Have you ever experienced this one? Or else you can consider if you want to cut your dress or whatever. So you will stretch it and you will start to apply scissor over it. Clear? What happens when we stress it? See, normally when we stress the material will be subjected to tensile stress. Clear? And this tensile stress will aid the material to propagate its crack easily. That is why we can easily cut it or we can easily break the material. Clear? So that is the disadvantages of the tensile residue stress over the material. So whenever we are going for the conventional fabrication techniques such as casting or additive manufacturing or whatever techniques you are going to make, finally the surface or the top surface of the material is going to end up with the tensile residue stress behavior. Okay, especially in additive manufacturing condition, since it is subjected to the varying heating and cooling cycle, so the end condition or the top end of the surface will be having a high range of or a high magnitude of tensile residue stress will be there. This tensile residue stress, in addition to the presence of pores inside the additively manufactured component, which aid the material or the crack to propagate easily. And as a result, the material will fail with respect to the application of small load. That is why we need to avoid, or that is why we need to change the behavior of this tensile nature to compressive nature. Clear? That is a fundamental aim or fundamental objective behind the laser shock peening process, we need to change the tensile resistance into compressive behavior from the surface of the material. Since the surface is going in contact with the mechanical components, especially when there is a relative motion between these two components. And you can consider when there is a piston, or you consider the camshaft, or you consider the rotor blades, or you consider the rocket engine assemblies. In these conditions, you know that there is a relative motion between these components. So whenever there is a relative motion, so this presence of this type of tensile resistance, which further enhances the crack propagation and finally result in the failure of the material, especially in the fatigue resistance of the material. When you consider the fatigue resistance of material, this type of tensile resistance will result in failure within short span of time. So that is why we are mainly concentrating on the compressive resistors, and that is the main aim behind the laser shock peening process. Clear? So in the laser shock peening process, which utilizes a high energy laser pulses to generate the plasma. So this plasma induced shock waves which penetrates deep into the material, and how much thickness it is going to affect, it depends on the process parameters that you are going to apply on the surface. Clear? So now it is clear that what is the need of laser shock peening. Am I correct? You may be, now you know what is the need of laser shock peening over the metal parts. Now next step, we know that the main energy source that we are going to use is a pulsed laser. Then next one is, we need to know what are the process parameters or how we can control, because we need to induce a compressive resistance over the surface of the material or up to a certain thickness. So that we need to understand how we can impart or how we can induce the compressive resistance in the material with respect to the process parameters. So if we induce the compressive resistance, which enhances the fatigue strength, wear resistance, the corrosion resistance, and its mechanism also, that is microstructural mechanism also, that is the grain refinement is also possible with the help of laser shock peening, and therefore it makes the material valuable for aerospace, automotive, then biomedical applications also. So especially in case of additively manufactured components, we know that there are certain defects associated with the parts and which are inherent to the process. Even though we optimize the process parameters, finally it will end up with some kind of defects. These defects cannot be completely removed from the metal parts. So we can use this type of post treatments in order to improve the service life of the material. So that's all about the laser shock peening of the laser shock peening process. Now I'm going to discuss about the methodology behind the laser shock peening process. Okay, now you look at this image. Now here you can see that this is a vertical image of your target material or the metal surface. So here another important thing is that in case of laser shock peening, we can use this surface or the material of any shape, like flat shape you can use, curved shape you can use. Clear? In case of turbine blades and all, if you want to peen a particular area or a surface, then you can use any kind of or any shape of surface, okay, irrespective of the laser power. So here you can see a vertical flat surface over here, the extreme right hand, and in between, next to the vertical surface, you can see a black layer. That is the, either you can use a PVC tape or you can use black carbon paint, whatever. The condition is that it should be of a certain thickness. That thickness, why we are providing a certain thickness, is to resist the thermal shock load or in order to avoid the shock of the laser shock peening process to the material. Then the left side you can see a blue colored layer. That is nothing but that is the confinement layer, or it is the water flow that we are continuously flowing through the surface of the material. Clear? Now we use a high energy laser source and we focused the laser onto the material surface by using different collecting lenses, and with the help of this lens, the pulsed laser is going to incident on the surface of the material, and as a result it is going to develop plasma. That is the condition. So depending upon the condition and depending upon the requirement, suppose if you want to peen a particular area, or if you want to peen a square area, or if you want to peen a normal fatigue test sample, if you want to strengthen the gauge area of your dumbbell shape, then you consider that particular area, okay. Or if you want to enhance the corrosion resistance of a particular square piece, then how do we proceed? We select that particular area. So depending upon your requirement and depending upon the area upon which you are going to peen the surface, you can select this dimension accordingly, okay. This is the dimension that I have taken for my sample. So this is selected, this dimension is taken for corrosion testing condition. So here these circular shapes, you can see the continuous overlapping circles you can see here. These are nothing but these are the laser shots, okay. And here you can see one thing is that there is no gap between the consecutive or the adjacent shots. Is there any gap between shots? No, it is overlapping type. So if you provide a space between the nearest or nearby shots, then what will happen? It will not deform the material, or we need to deform the material plastically, or plastic deformation is the requirement in order to introduce compressive resistances over the material. So if you want to provide, or if you want to get a fully plastic deformation condition, then you have to use overlapping shots regularly. So it can be either in the horizontal direction or in the vertical direction. The condition is that it should be in overlapping condition. The overlapping rate you can fix based on your requirement. It can be either 50% overlapping or 60% overlapping or 70 or 75. It depends upon the application. Again, we are going to peen the material surface from left end to right end, and is going to move in the left to right direction. And again we are repeating the same from right to left, then again from left to right. It is going like that. So it is a continuous peening operation, and we are following a certain condition or certain process parameters in order to get fully or effective peening. Clear? I will come to that. So there are certain conditions. Before we go for the laser shock peening, or before we select these process parameters, we should know what are the parameters or what are the conditions that we need to know before we apply a particular laser shock or laser over the metal surface. We cannot apply all the lasers directly in order to get a peening effect. So we need to know first the shape of the laser spot. So first one, the shape of the laser spot. So there are different shapes available depending upon the aperture size or aperture you can change. Depending upon the aperture or slit size, you can vary the shape of the laser. It can be either circular or square or elliptic in shape, but commonly in laser shock peening technique, industry people, they use circular spot. I will explain what is the reason behind it. Because the laser pressure, it follows, or laser energy distribution, which follows normal Gaussian distribution. That is why most of the cases we follow or we use circular spot. Then second parameter is the spatial energy distribution. So whenever you use a laser spot of a certain diameter, say like if you are going to use a laser beam of radius 1 mm or 2 mm or 3 mm, it is not a spot dia. If you are using a spot dia of 3 mm, that 3 mm area you are going to cover with the help of that laser. So that is how the laser is going to vary its, or how it is going to distribute the pressure or the peak pressure with respect to the radius. Whenever you are going to incident or whenever you are going to target the laser over the metal surface, it is going to contact at a particular point. Clear? From that point, the radius is going to increase with respect to time. So with respect to the increase in radius, the pressure is going to distribute. Clear? So that is the second parameter, that is a spatial energy distribution we need to know. So it follows Gaussian distribution function. So that is why Gaussian beams are used in the case of laser shock peening. And third one is spot overlapping rate. I have already mentioned what is the need of overlapping between the consecutive or successive shots. So overlapping rate is sufficient in order to, or the provided overlapping condition should be sufficient enough to produce plastic deformation over the material surface. Okay, I will explain it in detail. Then next one is the wavelength of laser that you are going to use. Suppose if your wavelength is very low, then it will not impart a high residual compressive stress, and the propagation of this high shock waves, if your wavelength is very low, then the propagation of this shock wave will be limited with respect to the thickness or with respect to the depth of your material. So wavelength is also a very important parameter when you are considering the laser shock peening operation. Then next one is the energy of the laser that you are going to use. Suppose if you use a high energy laser, what will happen to the material? Material will undergo plastic deformation with the help of the formation of plasma. Clear? So whenever we use high energy laser, the plasma pressure will be high or higher compared to the previous one, or compared to the lower density or lower energy value of the laser. Then that also affects, that also matters in the case of laser shock peening. Then the last one is the pulse or pulse width. See, I told you at the beginning itself that it is called laser shock peening, and here we use pulsed laser. So pulsed laser means the laser pressure is going to vary with respect to time. How it is varying means the laser pressure, or initially when the laser is going to get in, when it is going to touch with the material surface, at the time of contact, the pressure will be 0. When it is going contact with the surface, it starts to form a plasma or to generate a plasma condition. At that time, there is a time limit or the time required to reach maximum pressure. So that is known as pulse duration or pulse width of a laser. Clear? In the case of pulse laser, the pulse width is nothing but the duration, time required to reach the maximum pressure of a laser. Clear? Then if it takes a particular time t, that same time will be taken for reversing the direction. That means from the maximum value, it will come down to the minimum 0 bar pressure. So that is known as the pulse duration. It can be varied with respect to the condition of your laser. It may be either 10 nanosecond or 20 nanosecond or 30 nanosecond, depends on the availability of lasers. So these are the process, or these are the parameters which are related to the laser. Okay, now next one, we are going to study the laser process parameters in detail. The first one is laser power, second one is pulse width, third one is laser diameter or spot diameter. It's actually spot diameter, not laser diameter. Please correct it as spot diameter. Then next one is ablative layer, or it is a tape or black paint of thickness 3 mm. That is the minimum thickness that is required. So first I am going to discuss about the laser power. Okay, so the laser power, we need to know how the laser power is going to vary with respect to the selected condition. And if you are having a laser of a certain energy, you say your laser is having of energy 2 joule. Clear? And you are going to use that particular laser. But you need to know how much pressure it can develop, or how much pressure it is going to develop on the surface of the material, and how it is going to distribute with respect to the condition. That we need to know, or we need to understand. So the laser power is or the power distribution of laser is a function of the value R and T. I will explain what is R. R and T, where R is the instantaneous radius of your spot or the shot. Then T is the time duration. So pressure is a function of both radius as well as time. So P of RT is equal to P of R into P of T. That is the equation that we use to calculate the maximum pressure distribution over the surface. Then the first one is P of R, the pressure or the plasma pressure developed due to the laser shock peening is a function of, first one is a function of radius of this spot, or it is equal to exponential of minus r square by 2 into r square r0, where r0 is nothing but r0 is the radius of this spot or this shot, r is the instantaneous radius. Okay, initially r will be 0, at the end of the time r will be equal to r0. So that is the variation of pressure with respect to radius of the laser spot or laser shot. Then the second term, that is the variation of laser pressure with respect to time. It follows normal Gaussian function. So here you can see that there are 3 stages. First stage, when it touches or when it hits the surface of the material, initial pressure will be 0. So with respect to time, I told you that there is a time duration that is known as pulse duration or TD. Short term TD is used for pulse duration, and during that pulse duration time, say if example, if you consider a pulse duration of 10 nanosecond, within 10 nanosecond it will go to its maximum pressure. Clear? So plasma is fully developed over the surface and you are getting a maximum pressure of P max. That is your maximum pressure that the laser can generate. Okay, with respect to the condition. So you got a maximum pressure within TD time. That is the first stage. Second stage is that after obtaining the maximum pressure value, it is going to reduce its pressure to minimum value. Clear? Because after obtaining the maximum pressure over the surface of the material, it is going to impart or it is going to transmit through the material. And as a result, what will happen? The pressure will reduce to 0. Clear? And the pressure starts to propagate through the material with respect to the condition. So the second stage is pressure is going to decrease to the initial condition, that is the 0 condition. So the first shot is over. That is the first shot. Then we wait for some time, that is for the relaxation of the surface. So whenever you are using continuous shot peening or shock peening over the material, what will happen? Without giving any, without giving much time for the material to withstand that thermal expansion. So it has to come back to its original position, then only we need to give the another shot. So that is a time gap that we are going to provide purposefully for avoiding the thermal load variation over the material surface. Clear? It will deteriorate the material surface. That is why. So with the TD time, say TD if is equal to 10 nanosecond, normally it is a 10 nanosecond. 10 nanosecond it will go to the maximum value. In the second stage it is going to reduce to the 0 bar with the next 10 nanoseconds. So from 0 to maximum, maximum to 0, it takes almost 2 TD time, means 2 times its pulse duration. Clear? And if you are having a laser with a pulse duration 10 nanosecond, it means that it takes 10 nanosecond to reach its maximum pressure, and again the next 10 nanosecond, within the next 10 nanosecond it will come to 0 condition. So the third phase is nothing but the pressure will be 0. We are giving some time for capturing that shock wave. Clear? Capturing the shock wave to the material. So that time, that is the third phase, we are going to give 10 times TD. 10 times TD is the maximum or the minimum time requirement for relaxing or for getting the shock wave to transmit to the material. Clear? So for a single shot or single shock peening condition, you need to give total 12 TD. 1 TD for maximum peak pressure, then second TD for minimum peak pressure, and 10 TD means 10 times the pulse duration for the shock absorbing condition. So total you need to give how much? 12 TD. If your pulse duration is 10 nanosecond, 10 nanosecond plus 10 nanosecond, 20 nanosecond plus 10 times TD, it's almost 120 nanosecond is required for completing 1 shots. Is it clear? Okay, so that is the 3 phases. So corresponding to 3 phases, the values are pressure P of T is equal to T by TD of P max. When T, the instantaneous time, when T is equal to TD, your PT will become P max. Then when in the second phase, when T is equal to TD, it will become 2 minus 1 into P max. Then P is equal to 0 in the third phase. So this is the condition of the pressure distribution with respect to time. I hope it is clear. Coming to the, now we know, yes. Yes. Yeah, yes. So if you are having a laser with the pulse duration 10 nanosecond, so that 10 nanosecond is the TD. pulse duration of that particular laser. So it will take 10 nanoseconds to reach its maximum pressure. Again, it will take this another 10 nanoseconds to reach to minimum condition, that is zero condition. So that is the total time for maximum to minimum condition. Clear? Now we will give another 10 TD time, 10 TD time, that is the minimum requirement. 10 times TD that we have to give for allow the material to propagate the shock wave. Clear? So that is 10 TD. So if TD is 10 nanosecond, then 10 nanosecond is for first phase, 10 nanosecond for second phase, then 20 is there. The remaining what? 10 times TD, then 10 into 10 is 100, total 120 nanosecond. If pulse duration is 10 nanosecond, then total time for that particular laser is 120 nanoseconds. Yeah, we have to follow the same. Yes, yes. The thing is like with respect to the, if your material thickness is very high, then we have to consider another parameter, that is the laser power or power density of the laser. That I will explain in detail. Yes. This equation. Yes. Yes. See, when t is equal to 0, what will happen? 0. Is it clear? So it's a function, it follows this 0 to maximum condition. So time varies from 0 to TD. So it's a like integral form, 0 to TD. See, actually it is an integral form. I just changed it into normal conventional form. Actually it is like ESL is proportional to integral 0 to TD f of t into f of that. It's not easy to follow for some students. That's why I just changed it to the conventional way. Okay. Now, is it clear? Okay. Now we know that laser power is there. The condition is that we need to give 10 TD for relaxation and all. Now we know everything. But the question is that how do we calculate that maximum pressure? If I have a laser, a pulse laser with me, and I want to use that pulse laser for laser shock peening, then I want to know what is the maximum plasma pressure it is going to produce. Okay, so there is a well-known equation, it's known as Fabre's equation. So Fabre's developed the equation to calculate the laser plasma pressure. Okay, that equation is that plasma pressure P or laser plasma pressure P is equal to 0.01 times square root of alpha divided by 2 times alpha plus 3 into square root of Z into IO. It's a very known equation, especially for material science students. So this equation is used to calculate the plasma pressure. Okay, where the term alpha is nothing but alpha is the absorptivity of the metal surface. Clear? So if we use alumina, we know that alumina is having high reflectivity. Suppose if we use steel, it doesn't have that much reflectivity. So depending upon the reflectivity or depending upon the absorptivity of the material, the alpha value varies. Normally it varies from 0.1 to 0.3. Clear? And we can use these values with respect to the data available. A lot of data are available in literature. We can refer that values also. For steel it is 0.3 and for alumina it is 0.25. Depends on the material, values are available. And this next term Z is nothing but it is known as acoustic impedance factor. Acoustic impedance factor. Acoustic impedance factor is nothing but whenever it is a measure of how the laser pressure is going to impart over the surface of the material. And suppose if you take a metal surface and you are going to make a sound, howling sound here, how it is going to transmit through the surface. Okay, suppose if I use a, say like what you have done in your +2, that is resonance condition, you might have experienced resonance column or whatever. So when you may be experienced with a tuning fork and all. Yeah, so whenever you are disturbing a tuning fork, you can hear that sound, vibration sound, because that wave is transmitting through the material and you can hear that sound. And whenever train is coming on the rail, you can hear that sound far away from the train's position. Am I correct? So like that, Z is nothing but Z is the acoustic impedance of the material. And here we use the average value of Z with respect to the confinement layer as well as the metarget surface. Okay, Z is nothing, Z can be calculated as, so Z can be calculated as 2 divided by Z is equal to 1 divided by Z water plus 1 divided by ZT, where ZW is nothing but the confinement layer that we are going to use. Normally in laser shock peening we are using water as the confinement layer. Then ZT is the acoustic impedance of the target material or the material you are going to select. Suppose if you are going to peen aluminum, then aluminum is your target material, or you are going to use steel, steel is your target material. So the data are available in literature. So the peak pressure, P is in gigapascal, and alpha, as you know, it is the internal energy devoted to thermal energy. You will not be able to understand what it means. That is why I told you it is the absorptivity of the material. Then next one is Z. Z is a reduced shock impedance between target and confining water. So that we can calculate with respect to these values. And for the acoustic impedance value is the impedance value for water is it's 0.165 into 10 to 6 gram per centimeter square second. Similarly for water it is 1.5 into 10 to 6 gram per centimeter square second. That is the unit. Now if you know these values, you can calculate the maximum pressure corresponding to your laser. Clear? Now we know the condition, pressure distribution we know how to calculate the maximum pressure P or maximum peak pressure of your plasma. So now it is able to understand, or we can calculate all these values. Okay, now it is ready. Now I calculated the value. Then how do I ensure that it is going to impart the residual stress or going to impart shock wave to the material? How do I know? Is there any condition? Till now we followed whatever techniques that we have used in the laser shock peening. I just introduced the terms and you just followed. Now we know how to calculate the maximum pressure. We can calculate it. No issue. All data are with us. Now how do we ensure that this pressure, this particular pressure is going to impart shock wave into the material? So there is one more condition that you need to understand. I don't know how many of you know, how many of you heard dynamic yield strength of a particular material. Okay, it is related to dynamics. So it is simple. You can see this figure. I think it is clear. This second part, C. Is it clear? This figure? Okay. Now, have you heard of Huguenot elastic limit? Which you simply say elastic limit of the material. We know that elastic limit. We define that elastic limit within elastic limit itself, isn't it? We define yield stress within elastic limit. But here I am going to say that we are going to plastically deform the material. Clear? Whenever you are going to make or whenever you are going to generate plasma over the surface, this plasma is going to create plastic deformation over the surface. Clear? In order to get plastic deformation over the surface, what we need to do? We need to deform the material plastically. Clear? There is no elastic region. So there is a certain condition. The applied pressure should exceed a certain value. Then only the material will undergo plastic deformation. Am I correct? I will tell you what is that value. Whenever you are going to apply particular laser peak pressure, clear, and we know that this is the maximum pressure that we can apply all these things we know, but depending upon the material that you are going to select or depending upon the condition that you are going to do the peening operation, you need to know what is the dynamic yield strength of your material. Clear? Dynamic yield stress can be calculated based on the plasticity behavior or plastic behavior of the material. Okay, so here the condition HEL is nothing but it's the Huguenot elastic limit. That is the limit up to which the material behaves like elastic region or elastic. Beyond that value, material starts to form or material starts to deform plastically. That is HEL or Huguenot elastic limit. That is the limit, or it is also known as dynamic yield strength of the material. You might have heard of yield strength or yield stress or ultimate strength. These all are within elastic limit. Whenever we explain Hooke's law, we may say that, or we start with within elastic limit stress is proportional to strain. That is our condition. We start it with within elastic limit. Clear? But here there is no elastic limit. We are going to increase the plastic deformation. We are going to go above the plastic range or beyond the elastic limit. So that is the condition known as HEL. So when the applied pressure is, when it exceeds 2.5 times or when it exceeds 3 times HEL, then that type of pressure can be able to impart residual stress or shock wave into the material. Someone asked me about the question, irrespective of the material, how do we select these things? So this is the condition. Whenever you are going to select a particular laser or particular maximum pressure condition, you need to know the maximum pressure that you are going to apply on the material. It should exceed the Hugonostic elastic limit of the material, and it should be higher than 2 to 3 times. It should be higher, like it should be 2 to 3 times higher than the Hugonostic or HEL value. So I will explain it in detail. Variation of the pressure. So initially it is at 0 bar because there is no contact between the target material and laser. That is a 0 bar condition, and it is going to increase to P. P is what? The maximum pressure that we have calculated right now. Clear? So whenever it is going to increase, when it reaches sigma HEL or when it is equal to 1 times the dynamic yield stress value, what happens here? Materials, there is no change in its plastic strain. Is there any change? It is a straight line from here 0 to 1 HEL. When you cross the 1 HEL condition, material starts to deform plastically, or it starts to form plastic strain inside the material. Clear? Plastic strain inside the material. That is the term called, you might have studied, whenever you want to increase the hardness of a material, you need to go for strain hardening, isn't it? Or work hardening. What is that actually? We are going to give plastic deformation or plastic strain inside the material. That is the plastic strain, and the stress corresponding to that plastic strain is known as nothing but HEL. Clear? So that condition, so when it is equal to 1 HEL, it will start to deform plastically. Clear? When it is crosses 2 times HEL, see here, from here it starts to deform plastically. So here you can see this line. Okay, when it is reaches almost 2 HEL, it comes to a maximum plastic deformation. Here you can see a maximum plastic deformation here. Here the value of deformation strain EP is maximum. What happens when we go beyond this value? Again, there is no change in its plastic deformation due to work hardening, but the material starts to behave in the reverse order. That means material is going to give a reverse verb into the material, and that reverse verb is used to harden the material or induce the compressive stress in the material. So this is the condition. Whenever you are going to apply pressure, that pressure should be sufficient to deform the material plastically, or the condition is that the applied pressure should be greater than 2.5 to 3 times its HEL value. That is the condition. Yes. Within that time, pulse duration. Yes, yes, sir. Yeah. Yes, yes. That is the importance of pulse duration. Okay. And for alumina, I calculate it as 2.4 gigapascal. That is the dynamic yield stress value. And when we calculate a particular peak pressure with the help of 3J means 3, that is the energy density of the material. So I got it around 5.1 gigapascal. So that is sufficient for imparting the residual stress. But again, it depends upon the selection of your laser as well as its spot size. Now, so here, okay, I'm just skipping that video because I didn't get permission for that. So I just want to show that video, but I didn't get permission. Okay, now, so now we know what is the maximum peak pressure and how it is going to impart shock wave, what is the condition to impart plastic deformation, all these things we know. Okay, now how it is going to affect the mechanical properties. So first we study the fatigue life improvement of the metal parts with respect to the laser shock peening operation. Okay, so here we know that laser shock peening significantly improves the mechanical properties of the steel, aluminum, titanium alloys, then with the enhancement in its fatigue life, surface hardness, then compressive resistance, etc. where we have to concentrate more on how much depth it can induce the residual stress. It's very important parameter. Okay, so in fatigue life improvement, what we need to arrest? In case of fatigue life, in order to improve the fatigue life, we need to arrest the crack propagation. Clear? So that crack propagation we have to arrest by using the compressive residual stresses. Clear? Or we have to change the tensile region or tensile behavior into compressive behavior. That is the only possible way where how we can reduce the or we can enhance the fatigue life of the components. So here the first study that is conducted by Tang et al. He studied the high strength, the fatigue life of the high strength steel. So here you can see that the red line shows the improvement of its fatigue value in the tensile unit tensile test. So here it varies from 10 raised to 4 to 10 raised to 6. As we may be knowing, it is a high cycle fatigue range. So here the fatigue limit is increased to 448 from 417. So there is an improvement in the fatigue strength of the material with respect to the LSP condition in the case of high strength steel, and is giving almost 7.4 percentage gain at the 10 raised to 6 cycle. So here you can see that the variation at the 10 raised to 6 is almost 7.4 percentage variation is observed with the help of laser shock peening condition. Then the corresponding crack length. So that you have to be very careful whenever you are going to treat the surface with the laser shock peening. We need to understand how the crack is going to vary with respect to the peened condition or with respect to the peened surface to the bottom. So here we can see that. So in this study they have used multiple peening condition. That I will explain what is multiple peening. So initially you are having a flat metal surface with you. Clear, and you are going to peen from left to right or right to left, whatever way you want. You can follow either horizontal fashion or vertical fashion depending upon your requirement. There is no issue. But thing is that you have to follow the conditions. Clear. So once you have finished the peening operation, okay, now your surface is ready and it is undergoes or it is under plastic deformation condition. Clear. Now you are going to peen the same process again or the same surface or the peened surface. It is known as second time of peening, or it is known as double peening, or it is known as two impacts means that's double peening. So you are going to peen the surface once again. Triple peening means you are going to peen once more. Means 3 times you are going to peen the same surface. Clear? So that is 1 impact, 2 impact, 3 impact. You can see in some of the figures that 1 impact, 2 impact, 3 impact, which means we are going to peen the surface, single peening, double peening, triple peening condition. Clear? It is another process parameter that we are used to analyze the effective peening condition. Clear? Now here in this study they followed double peening condition, that is 1 impact and 2 impact. Okay, 1 impact and 2 impact. Here with respect or compared to the untreated condition, it is clear that the crack length as well as the life or the fatigue life is increasing with the number of impacts. In the case of 2 impacts, we can see that the fatigue life is increasing. So the fatigue life increasing with increasing the number of impacts compared to the untreated condition. So the crack length is or crack tip is increasing with respect to the loaded condition. So here we are getting a better life. Life means that propagation is hindered by means of introducing the compressive resistors. So whenever there exists a compressive resistors inside the material by means of LSP or laser shock peening process, this laser shock peening or the induced compressive resistors which further hinders the propagation or the motion of your or the movement of the cracks. So normally when we stress a material normally we can see that there's a branching of cracks will be there. But in case of LSP samples or laser shock peen samples, that branching will not be there because that branching or the crack propagation will be arrested by means of the compressive resistors by dislocation pileups. I will explain what is dislocation pileups. There's a term called dislocation strengthening. So in the next study, that is in the aluminum alloy. So there also they have studied that the right side figure shows that in the case of the untreated condition, the fatigue limit is around 152 plus or minus 7 MPa. So after the laser shock peening condition, after the laser shock peening, the value is increased to 183. So that much variation or significant improvement is there with the help of LSP shock peening in the case of 7075 T651 alumina alloy. And you may be knowing that 7075 is a high strength alumina alloy which is used in aerospace as well as automotive industries. It is a heat treated condition or solution treated material which is used for aircraft components. Then another, that is 7075 is a aluminium zinc magnesium alloy. Similarly 2024 it is a aluminium copper alloy. It is used for again in aerospace applications. So in these two conditions, these two materials, what we observed from the LSP condition or LSP treatment is that we are getting an improvement in the fatigue life. So especially these materials fatigue life can be improved with the help of this process, and thereby we can apply this material for specific conditions in aerospace. Yeah, yes, correct. So there's something related to material science. So I can explain that also if you're interested. I will explain it in detail, no issue. But I don't know how you can follow because my background is material science. So I can explain that in detail if you're interested. I will come to that figure. Okay, I will explain in detail because for the time being, I'm just telling it is known as dislocation pileup or dislocation strengthening. For the time being, just understand this is the term. Okay. Now, I selected these two materials because nowadays a lot of research is going on in this area, because nowadays people are thinking of, you might have heard of functionally graded materials or single crystal material. So all these kind of materials, but why they are looking at this kind of materials just to increase its fatigue life. So if we can increase the fatigue life by means of this type of LSP treatment, then it will be good, because we can apply this type of process on any type of surface, irrespective of its shape, size and all. Okay. Now, and in another condition, so in the second study, what they did is they just studied the fatigue life of this material with the pre-crack condition. So before testing the normal surface, they just cracked it. They just applied a uniaxial tensile stress and just cracks were formed over the surface, and they peened that cracked surface. Finally, they identified that after laser shock peening condition, so here there is an improvement in its fatigue life, which is 37% improvement is there compared to the smooth untreated condition. So whenever there is no crack inside the material, laser shock peening is going to give a maximum of 20%. But if there is a crack inside the crack is present inside the material, it is going to give a maximum of 37% increment in its fatigue life. Then that is the crack, if there is a crack is there, so it is known as dislocation or kernel average misorientation. Misorientation is the term. I will explain it in detail with respect to the crack condition. So it is known as kernel average misorientation or CAM value. CAM value is nothing but when grains are going to align with the lower angle grain boundary, higher angle grain boundary, medium angle grain boundary, different grain boundaries are there. So depending upon the grain boundary condition, if it is lower angle grain boundary, it will not allow you to move away, or it will not allow you to move from one position to another position. Suppose if I locate some of you, 500 people, if I place, if I group you 500 people over there with a short space, then you cannot move away from your you cannot move away from your nearest position, because you are that much hindered or that much you are blocked. Okay, it is known as lower angle grain boundary. You cannot move. The grains are oriented in small angles, and as a result, it will further hinder the crack propagation. If crack is there, further the grains are oriented in that particular direction, it will enhance the crack boundary. Tip will, then another term is called crack tip, or the crack tip will reduce with respect to the formation of smaller angle grain boundaries. Okay, something related to material science. Okay, not an issue. Okay, next one is the formation or the improvement in the compressive residues. So here, in the case of 316L, that is austenitic stainless steel and high chromium molybdenum steel. Here we can see that with respect to the laser shock peening condition, the resistance is going to increase and the depth of the residual stress, it is much better with respect to the condition that we are going to apply. Here you can see the untreated condition, the residual stress, that's the green line shows the untreated condition. So here, if the residual stress value is very close to positive region, which means it is a tensile residual stress. If the residual stress values are negative, which shows the presence of compressive residual stress. Okay, normally we use positive value for tensile and negative value for compressive value. So here, these red lines, where these are very close to minus 600 range at 0. 0 means the near surface. So near surface means when you are going to peen the surface, that is the surface or the near surface, the peening effect will be maximum. Okay, at that point, the compressive resistance will be maximum. So whenever you are going to study the depth of your material with respect to the peened condition, the resistance will be varying or the compressive value will be decreasing with the increase in the depth. So that is why we are getting a increase in the compressive value, which means compressive nature is going to change into tensile nature. So here all the values are within compressive range or compressive region only. For a maximum depth of 1 mm can be visible from this figure. So in the case of stainless steel, maximum 1 to 2 mm thickness is possible with the compressive resistors. Now next one is aluminum. Aluminum also exhibit the same phenomena. So the compressive resistance is maximum, it is possible up to a minus 250 nearby surface, and it is going to increase with increase in number of increase in the depth of the material from the peened surface. And the first two figures shows the FEM simulation of the residual stress with respect to the different condition, the different laser power they used, and it shows that anisotropy is there in the residual stress value with respect to the increase in laser power. And similarly, they calculated with the different impacts also, and maximum they observed with the second condition, that is the 3 times impact. So they observed that with the help of 3.8 joule, this middle one, 3.8 joule maximum residual stress is possible in the case of aluminum alloy. Similarly, they measured the compressive resistance with the help of XRD also, and finally they measured the micro hardness. In the case of micro hardness also, the maximum hardness value or dislocation pileup is happening with the help of increasing the power. So when we increase the laser power, we can get a maximum micro hardness, but the residual stress varies with respect to the increase in laser power. So that is the result of the aluminum alloy. Then in the another study, A.K. Rai, he has conducted a lot of studies based on steel as well as aluminum alloys. So in this recent study he conducted with the P91 material, which is mainly used in radioactive element or radioactive components. So here he identified the surface residual stress with respect to the variation in the laser power density. So different laser powers were selected depending upon the condition, and it was clear from this figure that in the unpeened condition, the surface residual stress were almost tensile in nature along the axial direction as well as the transverse direction. But after imparting or after the laser shock peening operation with a different laser power density, with respect to the increase in laser power density, the residual stress or the compressive residual stress is increasing. And this red line shows the compressive residual stress along the transverse direction. Suppose if you are going to peen in the horizontal direction, the transverse direction it will be maximum, and the black line shows the along the axial direction. Similarly, for this corresponding, that is for 3.9 laser power density, he calculated further with the single peening, double peening and triple peening condition, and observed that along the transverse direction maximum if it is possible with the triple peening condition. So that is the observation from this literature. And corresponding variation in the surface residual stress with respect to the distance across the peened surface. Suppose if you have a surface, your surface is like this, and you are going to peen entire area, and if you want to measure this cross section, suppose if you want to peen from here to here, and you are going to measure the residual stress here, here you are getting a residual stress of minus 620, and here you are getting a residual stress of plus 200. What does it mean? This peening is not effective throughout this area. Okay, so in order to study the effect of or the distribution of compressed residues, he just studied the variation of these residues over the surface or across the surface and measured the variation. So here, in this case of triple pin condition, the variation is not much significant and is giving a uniform variation or uniform distribution of compressed residues over the surface. So compared to the untreated condition, this is the untreated condition. Then similarly, the variation of the residues with respect to the depth of the peened surface is measured and maximum value is obtained with the triple peening condition compared to the untreated condition. And this is about, sorry, I am not sure that whether it is able to visible. So this is about the surface roughness variation compared to the short peening condition. Whenever you are using bullets or shots in the case of short peening condition, it is going to give mechanical deformation over the surface and is going to give some craters or some kind of pits over the surface, and finally it will result in increased surface roughness. But in the case of laser shock peening, since we are covering this entire surface with a carbon tape or a black paint with a certain thickness of 3 mm, and it is protected from this kind of deformations as well as this type of pits or craters, so the surface roughness will not be varying that much compared to the short peening condition. But anyway, whenever you are using laser shock peening operation, there is a possibility of variation in surface roughness, but there is not much variation, or that variation will not be significant compared to the other peening conditions. So here in the 7075 aluminum alloy, so the surface roughness slightly increased from 1. I can read it. It is, so in the untreated condition it was 1.9 and surface roughness, average surface roughness increased to 4.2 with 2.6 joule in the triple peening condition. Similarly, when we increase it to the same condition, that is 2.6 joule with a single impact, it shows value of 3.7. That means with respect to the increase in number of peening, the surface roughness increased. Similarly, when we increase the laser power to 5 joule from 2.6, with a single impact itself, it shows micro pits and debris over the surface. That means whenever you are going to increase the laser power, it is going to make pits over the surface, and this pits further deteriorates the surface, and further it will reduce the wear resistance of the material also. Yes. That is, yes. That pits will form if you use a high laser power, because if it is very small pulse duration and you are going to use a very large power, that dynamic plasticity, it is known as plasticity index. I don't know how many of you are aware of plasticity index of the material. It's a term called plasticity index. If the plasticity index if cross beyond 1, then material will deform. That is, localized plastic deformation will take place. This type of localized plastic deformation which creates this type of pits or micro pits. Okay, so we have to be very careful when you are playing with the laser power density as well as the pulse duration. So if you are having a pulse duration of 10 nanosecond, better you have to go for, or you have to think of a lower value of energy or laser power density. Suppose if you are having a higher value of laser power density, then you have to think of a sufficient time to increase that plasma pressure. So that is another condition. So thank you for your question. It's a good question. Now, surface roughness increased with respect to the peening condition. So in the case of another material, that is in the case of stainless steel or normal conventional stainless steel, here also we can see that the average surface roughness value increases. This blue line shows the Yes, this blue line shows the average surface roughness or the variation of surface roughness of the untreated sample, and the second figure it shows the variation of the surface roughness with respect to the LSP condition. This red line shows the variation of its roughness value, and here you can see that the roughness RA value is increased from 0.14 to 0.5, 0.95 to 2.28 in RZ. Similarly, SA and SZ value is also increasing with respect to the peening condition. So we cannot say that the surface roughness is it is not going to smooth surface, it is going to increase the roughness of the material, but there is no much variation in the surface roughness compared to the other peening condition. Similarly, in P91 material also, here you can see the surface of the peened sample of P91 material. Here you can see that type of texture over the surface. So that whenever we are playing with the pressure, laser power density as well as the pulse duration, you will get this type of effective peening. Suppose if we use different pressure or different power density and with a different spot diameter is also very important, 3 mm, 2 mm, 1 mm. So it will make some surface damages also. So depending upon the condition or optimizing the process parameters, you will get a better peening over the surface of the material that you are going to select. So here also the variation of the surface roughness is not much significant in the case of P91 material. So here they have applied an optimized process parameters. So this work is done at RRCAT in Tor. Now, so this is about the mechanism, that is the grain refinement and micro harness. So I told you before, so whenever we are going to give laser shock peening over the surface, micro harness is going to increase. The micro harness mainly increased due to the increase in dislocation pileups. Dislocation pileup is nothing but here you can see that this is the image of the steel. Here there are a lot of lath martensite is there, but when we go for the LSP treatment, some kind of dispersions are happening over the surface. Dispersion means the carbon is going to disperse or the chromium is going to precipitate over the surface of the material, and that is a kind of precipitation hardening mechanism that is happening inside the material. So the peened region, we can see that type of precipitation hardening is there, and due to this precipitation hardening, the hardness of the material is also increased. So here you can see that result here, hardness is increased with increase in laser shock peening condition. Similarly, here also you can see that the aluminum alloy, some nanoscale precipitations are over there. So in the second figure, that is figure B represents the martensitic formation. So here also we can see some kind of, these B, C are the TEM images of the samples after laser shock peening operation. Here you can see some precipitations here, and here also you can see the dislocations, 0.1 and 0.2 are dislocations. So along the grain boundary, some high dense dislocations are visible over the surface. Some dark portions you can see over here. And here also, along the grain boundary condition, you can see some nano precipitations over this area. So whenever there is nano precipitation or precipitation of the material along the grain boundary, it is known as grain boundary strengthening. Again, it is going to increase the hardness of the material, also the crack propagation. Okay, so that is known as grain boundary precipitation or grain boundary strengthening of the material. Again, the grain boundary, if it is a long grain boundary, it is like large grain boundary, and inside the grain boundary there will be a number of grains or subgrains will be there. If the number of subgrains are more, then it is known as lower angle grain boundary. If the number of subgrains are less, it is known as higher angle grain boundary. If number of grains inside or subgrains inside the grain boundary is higher and LAGB means the fraction of lower angle grain boundary is higher, then it will not allow grain boundary or material transfer to or slip. It is not a slip. The dislocation can slip from one grain boundary to another grain boundary. If the grain boundaries are strengthened by means of this nano precipitation, as well as there are a number of small subgrains, small lower angle grain boundaries are there, then dislocation cannot slip from one grain boundary to another grain boundary. Therefore, the crack cannot propagate. Thereby it creates a tortuosity path. It is like a tortuosity path. It cannot, so it has to deviate from that particular direction. So when it is going to deviate or the crack is propagating, so whenever it meets at a particular grain boundary, since the grain boundary strengthened or is known as grain boundary density is higher, and it cannot transmit or it cannot propagate further. And as a result, what will happen? It will deviate its path. So whenever it is going to deviate its path, some amount of energy will be absorbed by these grains. Okay, therefore the driving potential is going to reduce with the help of this type of presence of the grain boundary or grain boundary precipitation. Clear? So that is actually what happening inside the aluminum material. Now similarly, he studied the variation with respect to multiple shots. So it is the nearby area where you can expect severe plastic deformation, where the deformation will be very high, and you can see the dislocation pileup as well as dynamic recrystallization also. Dynamic recrystallization is going to happen when the grains are annihilated. Annihilated means when the grains release its energy, so it is going to make subgrains. So it is known as annihilation. So this is the mechanism actually happened here, and corresponding hardness also measured, and the hardness is increased with the maximum with the triple pin condition. This upward triangle you can see here, the maximum hardness is observed with this condition, that is the triple pin condition compared to the unpinned condition. This is your unpinned condition. Okay, and the maximum value is increased with the maximum depth, see, up to 500 micrometer, the hardness value is just above the unpinned condition. Okay, so the maximum hardness is obtained up to a maximum depth of 500 micrometer in the case of the P91 material. And similarly, the wear resistance of the material also measured with the help of different laser power density or laser power energy, 2 joule, 3 joule and 4 joule. Here it is clear that from this, the micro hardness is increased with the increasing the energy of the laser. So this red triangular line shows the maximum hardness with respect to the 4 joule laser power, and corresponding corresponding resistances also you can see here. Maximum resistance is observed in the case of 2 joule. That is the contradictory result. So maximum compressive resistance we observed with the help of 2 joule, whereas the micro hardness is increased with the increase in number of laser power. These are the microstructure or the microstructural changes what is actually happening inside the material. Okay, so whenever there is a presence of a compressive resistance, it is going to increase the strength of the material. But whenever there is a change in its microstructure, like a subgrain or grain refinement, which will further enhances the hardness of the material, and thereby enhancing the wear resistance of the material as well. So here also the right side, that with respect to the number of shots or with respect to the laser shock peening process, the wear volume is decreased to 16% in the case of first shock times, and second shock time it is much increased to 40%, and finally it is reduced to 33%. Anyway, from this result it is clear that with respect to the LSP condition, the wear volume is going to reduce, and this graph, this line, this pink line shows the variation in its width and depth of the worn track. I couldn't add that one here due to the time constraint. Now, this is the mechanism what they have identified from the P91 material, as I told you before. So, whenever we are going to impart plastic deformation of the surface of the material, there is a creation of dislocation due to this LSP. So, dislocations are going to increase with respect to the increase in plastic deformation. Okay, that is known as dislocation strengthening. Then after some time, what is happening? Beyond that, dislocations or the formation of dynamic dislocation walls are going to form. The dislocations are going to arrange in particular directions. Finally, it will result in dislocation walls. Then after some time, when we are going to give further deformation, or if we are going to deformation or the plastic deformation in different levels, like a single peening, double peening or triple peening, then the further plastic strain, when you are going to increase the strain again, the material is going to annihilate. Annihilate means it is going to reduce its it is going to reduce its strain value, and as a result it is going to make crystallization region or crystallization of the grains, or it is known as subgrain formation. So here after annihilation, what is happening? This area is going to divide, or the formation of subgrains are going to form. These lines are known as dislocations or twins. You might have heard of twin boundary, tilt boundary, all these are dislocations. So here it is mainly induced mainly due to the twin boundaries. Now this is actually happening. What is the strengthening mechanism in FCC, HCP and BCC? So this is a general idea. From this figure, you can read what is actually happening inside the material with respect to the LSP condition. Okay, in FCC, SCP, BCC, these details are available in this particular journal. You can refer it. It's a very good journal. So if you have free time, you can refer this one. It's an interesting result. So based on precipitation hardening and based on the the grains, orientation, refinement, all these processes are happening inside the material, and as a result, the material is going to increase its strength. So it's very interesting result. So aluminum as well as stainless steel are FCC in shape, FCC in structure. So that is why I explained these things. The remaining two, HCP for titanium and BCC, you can, martensitic steel, all these cases you can consider these two. So these are the main mechanism actually happening, the dislocation pileups, then precipitation hardening, and the residues. These are the main three reasons which enhances or which strengthens the material after the LSP process. That is why we are getting better fatigue resistance, better wear resistance, better hardness, better corrosion resistance as well. Because if there are number of, depending upon the fraction of lower angle grain boundary always resists the nucleation pits, and thereby enhancing the corrosion resistance of the material. My study was mainly focused on that area, so I did a lot of good research, but this paper is under review only. So I hope that you will publish in 1 to 3 weeks. So I couldn't disclose that one. So next one is compared. So since we have already explained what is actually happening to the conventional material. When we go for the LSP on the conventional material, we may get better surface qualities, better mechanical properties as well. But in the case of additive manufactured components, what is the need of laser shock peening in additive manufacturing process, or why do we consider the LSP as a post-treatment process in the laser shock, in the additively manufactured components? So we know that there are certain defects associated with these additive manufacturing components, especially the porosity, surface residue stresses, that is the tensor residue stress. Then third one is, any idea? First one is porosity, second one is tensor residue stress, third one is roughness. So these are the main defects associated with the additive manufacturing parts. We can minimize this effect to some extent by optimizing the process parameters. But even though if you optimize the process parameters, you cannot minimize this effect fully. So that is a problem. These are inherent to the parts. Okay. So if you want to improve the properties better without compromising the mechanical properties, normally we say that when we go for the additive manufacturing process, we may get, or we may end up with a part with the significant properties, or we may get a better or excellent property compared to the conventional material, conventional counterpart. So we always specify that improvement in terms of mechanical property. We are getting better mechanical property, but other properties like if you want to measure its surface hardness or its plasticity, or if you want to study the corrosion resistance or wear resistance, or if you want to study the material dynamic behavior, okay. So in that way, you have to consider, or you have to go for the you have to go for the laser shock peening or different type of post-treating technique. But if you go for another technique, suppose you might have heard of different other techniques, like if you go for a heat treatment process, or if you go for a hard anodizing process, or if you go for surface coating techniques, different techniques are there. But after a certain time or time interval, that coating or the layer that you are going to coat or the surface will delaminate over the time. So if you go for a better surface treatment or reliable surface treatment like LSP or laser shock peening type of surface treatments, it is going to change the inner subgrains, or it is going to change the material structure, and as a result you are getting a better property, and it is going to last for a long time. That is why we are getting better service life compared to the other techniques or other surface treatments. But normally when we go for heat treatment techniques, what is actually happening is, it is due to the thermal degradation. The grains or the matrix may weak its strength, or matrix may some amount of, say for example, I am considering aluminium ALS 10 mg, aluminium silicon magnesium alloy. It is a fine network of silicon, or a silicon network is surrounded with alumina, or alumina silicon rich alumina matrix is there. So when we are go for heat treatment operation, the silicon is going to coarsen, or it is going to precipitate from its matrix to the grain boundary, and as a result the matrix strength is going to reduce. Finally we may end up with a less hardness. when we go for heat treatment. So, but in this case, we cannot compromise the other properties. Once you optimize the process parameters in additive manufacturing process, and you end up with a very good property like mechanical properties. And if you are going for this type of surface treatments, you may end up with, or you may get better surface qualities as well, without compromising the mechanical property or without compromising the other properties of the component which you obtained through the additive manufacturing process. So the first one is porosity. Even though the porosity is mainly due to the incomplete combustion, then melting, the trapped gases, keyhole defect, these are the main reason for the porosity associated with these parts. So we can optimize the process parameters and we can increase the part density, improve the mechanical strength, then improve its wear resistance, enhance battery strength by means of using higher laser power, laser low scan speed, then high spacing, then layer thickness we can adjust. All these values we can adjust. These are the data which I have developed from my research only. So you can use this one if you are, any one of you are interested to do additive manufacturing process, you can make use of this data. Then similarly roughness. So in the roughness also we can reduce by laser power and spot size. Then powder size, particle distribution also we can use different variation. 10 to 45 micrometer will give you a better surface finish. Reduced layer thickness also from 20 to 40 micrometer range will give you a better surface finish. So these are the remedies. Then coming to the tensile reducers, preheating the build platform, lower cooling the rate, then modifying the scan package or scan strategy. Normally we may follow 0 degree or 90 degree or 45 degree, 60 degree. These are the different raster scanning techniques that we use in additive manufacturing. But 67 degree scan pattern will help in reducing the residue stress. But there also there is a variation or anisotropy in the property of the component with respect to the depth or with respect to the layer thickness. So we have to use the surface treatment techniques. So this is a recent study published last month, last year. So here they developed this one, aluminum alloy. That is a 2319. It's a standard aluminum alloy. They developed this type of alloy using warm technique, wire arc additive manufacturing technique. So after completing the wire arc additive manufacturing process, they applied the laser shock peening over the gauge length of these dumbbell shaped samples. And finally, they found that the surface, in the as-built condition, surface consists of different types of pores over there. Different textures were there and different size and shape of pores were visible over the surface. After the laser shock peening operation, you can see that if figure B1 shows that there is a change or there is a number of pores are reduced. Then in the further LSP, if you increase the laser power from 5 joule to 10 joule, you can see that there is no visible pores are not observed over this 10 joule condition. Similarly, the metallographic nature or you can see the cracks formed. Here the as-built condition, the size is very large, but when we go for 5 joule and 10 joule condition, the closure or this is known as pre-closure of the pores. Okay, now that is also possible with respect to LSP. Coming to the microstructure, you can see that the grains texture and grains orientation which we can measure with the help of EBSD analysis. So the first figure shows the inverse pole figure analysis, so which clearly explains the orientation of the grains, and there is no much variation in the orientation grain after the LSP and as-built condition. But only thing is that in the case of additive manufactured components, irrespective of the method, it will be like long columnar grains. But in the case of LSP sample, the nearby region of the LSP sample, it will show refined grains, and which will not be a long columnar grain, it will be a refined grain. So that this is the refined grain size. You can see some globular shape over here, but here you can see somewhat it is stretched. But after LSP process, it is like almost spherical in shape. And the second graph is CAM, that is kernel average misorientation graph. It is an indication of how much or how the grains are aligned inside the subgrain, or it is the measure of misorientation grains inside a grain. So CAM value is going to increase with, here you can see that yellow color is increased, so this which shows the increase in the misorientation angle of the material with respect to the laser shock peening condition. And here also LAGB, HAGB is also visible with the as-built condition. See, HAGB is higher compared to the lower angle grain boundary. The HAGBs are prone to corrosion also. So if you want to reduce the HAGB to LAGB, that is lower angle grain boundaries, it is possible to reduce the, it is possible to reduce the higher lower angle grain boundaries increased to 50% in the case of 5 joule, and it is going to increase with 51.2. Maximum is observed with the help of 10 joule, so that we can increase the grain boundary distribution also, which further enhances the strength. And the right side figure shows the pore number and its diameter with respect to the peening condition. And it is clear that the pore size is reduced with the LSP 10 joule condition compared to the first one. That first one is the as deposited condition or as printed condition. Similarly, the corresponding hardness and resistance value is also measured. Here you can see the hardness value is higher in the case of 10 joule and 5 joule compared to the as built condition. Similarly, the compressed resistance also increases with the increase in the laser power, and in the as built condition it's almost tensile in nature, but in case of laser peened surface, it is going to increase a maximum of 140 compressive resistance. Now the material properties also increased. The mechanical property, yield strength as well as ultimate tensile strength is increasing with increase in laser power compared to the as-built condition. And fatigue life also increased with the increase in the laser power in the case of the material. So in the case of aluminum alloy, we can say that the laser shock peening is going to improve, or it enhances the fatigue life. It improves its hardness, then lower angle grain boundary fraction is going to increase with the number of impacts, which also helps or which mitigates the pitting as well as the corrosion, stress, cracking, especially in marine as well as aerospace environments. Then grain refinement also possible with the help of this LSP, which refines or which improves the mechanical properties of the components. The main challenge associated with this laser shock peening is that the sensitivity to laser parameters, that's what we have starting we have explained. There are different parameters. We have to select properly in order to get better peening effect. So that sensitivity to laser parameters and potential thermal effects, which affects the surface phenomena, surface properties also, surface qualities also. So we have to be very careful when we are dealing with the process parameters as well. Now coming to the stainless steel alloys, again we are getting better surface hardness, improve the fatigue performance, enhance the corrosion resistance. Microstructural modifications also possible with the grain refinement of the peened surface. And main challenge is that when we go beyond this surface, suppose if you use a thin sheet, what will happen to the laser shock peened surface? Suppose if you use a very thin sheet, say like 0.5 micrometer, and we can say that the laser peening effect is going to give a maximum effect within 1 to 2 millimeter. So whenever you are using a very thin sheet, what will happen to the material? The other side, when it passes through, when the shock wave passes through the material, it is going to break the material when it is a very thin sheet. So very thin sheet is also possible. The only thing is that we have to peen the other side also. Okay, that is the method or the remedy which we can follow in the case of thin sheets. So these are the references. We can follow this one. So if you have any questions, you can ask. Thank you. Yes.
Microfits might be formed. In case of that overlapping spots, will that micro pits turn to craters?
Yes, exactly. I forgot to add that point here. So whenever you use, that is the strategy behind the selection of the overlapping rate. It is known as overlapping frequency actually. So repetition rate also. Suppose if we use continuous shots or continuous laser shots, you have to follow either 50% overlap or 60% overlap or 70. So it depends on how the pits or micro pits are going to form over the surface. So by experience only you can optimize these things. Normally after several trial and error method, some of the researchers or some of the scientists, they have already optimized it to 60% along horizontal direction, 80% along vertical direction. These are the optimized data based on the material. In some literatures, it was clearly mentioned that they follow 60% overlapping along horizontal direction and 75% overlapping along the y direction or vertical direction. That is the minimal condition required for better surface finish. Okay. I hope you have understood the basic concepts actually. What is laser shock peening at least? If you have any suggestions, you can tell. Yes.
Here actually we are not melting any surface, right?
No, no, no.
It is just to provide that shock wave.
Yes.
So can we use the other methods like water jet if you use them?
We are using water jets continuously. We are flowing the water over the material continuously.
Instead of laser,
Ah.
you are impinging laser, right?
Yes.
What if you impinge that water jet, like water jet machining is there?
Yes, yes, yes.
Instead of that,
Water jet machining is different because our ultimate aim is to impart shock waves through the material. Clear? We need to get the plastic deformation. We need to give dislocation pile up inside the material. That is the ultimate aim of our laser shock peening. Then only we can impart compressive residual stress. Clear? But in case of water jet machining, it's a kind of machining process. What actually happens in water jet machining?
no, in laser, we also, that in mechanical laser machining is also there.
Yes.
But you are using their shock wave, right? So in water also we can use their means pressure to.
Yes, we can use water, but when we use water, what actually happens is it is going to damage the surface of the material. Clear? So here we don't want to give any damage to the surface because we are going to deal with the final components. Actually, this type of laser shock peening treatment is used for the actual components. Clear? For repairment application only we are doing this kind of process. So once you have a damaged part in your rocket or rock ram assembly, whatever, wherever you have some problems, you are going to increase the strength of that particular area. That is why we are going to give laser shock peening over a small area or a curved flat area. Depends upon your requirement. So there we cannot compromise any other properties. You're getting my point? So if you go for water treatment or water jetting process, it may affect some other properties also. But here we cannot compromise any other properties. That is the main reason behind why industry is adopting the technique is, if you go for laser shock peening process, you don't want to worry about the other properties. Like there will not be any change in other properties compared to this previous
Laser
condition.
shot pinning, is it commercialized or?
It is not commercialized. No, it is commercialized actually, but due to its cost, we cannot approach because some of the industry, including DRDO, ISRO, and RRCAT Tintor, they are having this facility, and they are using it for repairment action and repairment for the aircraft components. But we have to develop individually developed lasers are required for using this one. Otherwise, it is very costly.
So is it time consuming? Like suppose I want to short pin of 1 square area. So how much time?
No, no, it is not, that much time is not required. Actually, for it is the number of shots we need to first calculate based on the requirement. Suppose if you want to pin an area of 1 meter square, you have to identify how much pins, like as he said, we need to identify number of shots we are going to pin over that surface. And depending upon the pin, first we need to fix what? The overlapping condition. So depending upon the overlapping condition and laser spot diameter, you need to identify how many shots are required for covering the entire area, your entire area, along the horizontal as well as vertical direction. So depending upon, see, as I told you, 120 nanosecond is, suppose if your laser pulse duration is 10 nanosecond, so you will take only 120 nanosecond for completing one shot. Similarly, if you are having 100 shots, 10 shots along horizontal and 10 shots along vertical direction, total you will be having 100 shots. How many time it will take? Just count.
So you showed one some image, right?
Yes.
So it is 10 nanosecond to reach the peak pressure. Then
It is not 10 nanosecond. Suppose if you are using a pulse laser with a pulse duration 10 nanosecond, then it is 10 nanosecond.
Okay.
Otherwise, it is known as pulse duration TD.
So that extra 100 nanosecond, is it a dwell time?
Yeah, it's actually a dual tape.
But there you showed only peak point actually. That is only point actually. It should be some kind of dual.
It's dual only, where pressure is zero, no?
Pressure is 0.
Pressure is zero. See, once the peening operation is over, then there will not be much pressure over the surface. It is already transmitted to the surface, and the wave started to propagate through the material. At that time, there will not be any pressure over the surface. Clear?
No, there
Material has absorbed the shock.
Can you show the triangle?
Yeah, yes.
Is there?
This one, right?
This one, sir.
Yes.
Here actually it is from TD,
Yes.
right? The TD is 10 seconds, then 2 TD is 20 seconds.
Yes.
In total. But you are saying about 100 nanosecond also.
Yes. That is the remaining time. So from here, actually there is a red line is there. We cannot see it.
Okay.
So this phase, that is second phase starts from 2 TD to some more time.
So that is complete one
That
cycle.
is the delta.
That is complete one cycle.
Now, the entire cycle completes from 0 to that time. That is the one cycle.
Okay.
Total time. That is why I explained detail. That is, suppose 10 nanosecond is the pulse duration, 10 nanosecond for maximum to reach maximum pressure. Again, 10 nanosecond for next reach, like complete the second phase to 0. Therefore, the plasma is completely transferred to the material. Now, we are going to give relaxation time for relaxation time as 100 nanosecond. That is the total cycle. That's why I calculated as 10 plus 10 plus 100, around 120 nanosecond for a single shot.
Okay.
Clear?
Okay. So there is no dwell time of that laser to absorb the shock or something.
No. Nothing is that. That 10 nanosecond is the time for releasing.
Okay.
From top pinned surface, that is known as nearby surface to the next layer. That is the time required 10 nanosecond. Within 10 nanosecond, it will absorb. That material surface will absorb the laser shock waves.
One last question means how that plastically it is deforming. Means
Plastic?
how that waves are deforming plastically. You are saying that plastic deformation.
Yeah, it depends. See, have you heard of dynamic yield strength of the material, dynamic or plasticity?
Yes.
Your background is
Mechanical actually. I am from
Mecha-
mechanical.
mechanical.
Yes.
Okay.
So yield strength only we have.
Yield strength is not see, yield strength means that is like we are going to stress a material, like suppose we are going to test the tensile strength of the materials. What we are going to give, we are going to stress, or we are going to stretch it by using a dumbbell shape. Clear? And we are going to give a small strain rate, and when we apply load, it is going to give you a instantaneous strain with respect to the stress. Clear? And finally it is going to break beyond its yield point, or beyond this rupture or breaking point, ultimate point. I am telling beyond that there is a region. That is known as plastic region. We are going to, but here, since we are continuously stretching it, we are not getting sufficient time to consider that plastic region. But in this case, we are going to introduce that plastic deformation or plasticity over the surface or along the thickness of the layer. We are going to introduce the plasticity in the material. It's not like tensile stress. It is like it is going to vary, and that's why I told you in case of tensile test, what is happening? Volumetric strain is there. Due to this strain effect, what is happening? Material is going to deform along x direction, y direction, z direction. Finally, it is going to deform, and cup and cone is going to form, like, or rupture is going to form. But here there is no deformation actually. Means material is not going to deform permanently, but we are allowing the material to be in plastic deformation condition. That is known as plasticity.
Okay.
Clear? Within plasticity, we are playing with the material and we are getting maximum stress value. It is known as work hardening actually.
Okay.
You might have observed that the chisels are making very hard, no, by applying large force. Clear?
Yeah.
What we are doing actually, we are plastically deforming the tip of the chisel, right? That is the plastic deformation we are giving. But it is not breaking actually.
Right.
We will not allow it to break. Yes. But we will apply maximum deformation on the material. Then only the hardness will improve. But beyond, there is a limit. Beyond that limit, when we continuously apply that material, continuously apply the material to undergo plastic deformation again, what will happen? It will finally break. So there is a limit, like what we studied in elastic limit. There is a limit in plastic region also. That is known as plasticity of the material. Clear? It's related to design, design also. I think somewhat you understood, no?
Yeah. Thank you.
You have to study plasticity of the material, crystal plasticity. It is known as crystal plasticity. Yes. Again, now you ask question. Question is like, we compare shock peening with the laser short peening. Clear? Which one is better? So again, depends on the requirement. If you go for short peening, bullets, or you are using metal shot, say like 2 mm, 1 mm shots, you are going to for the surface, finally going to give a deformed condition, and roughness is going. The effect is going to, you are going to maximize your thickness or your depth. That if that you are going to high depth compared to here, the maximum effect you can produce up to a thickness of 2 mm. Consider the laser, laser short, your peening condition. It will better or better fatigue also. So again, if you want to concentrate on some qualities and some properties of the particular material or component, for example, land of your aeroplane, which you are going to apply, can you laser this one short peening? It's not possible. When we apply short peening, it will deteriorate, and finally it will lamination, start to delaminate from the there. You have to apply laser. Depends on the also. So we cannot say that technique is but no, it depends on the application and the requirement. No, we can shape also. Actually, we have done a lot of samples over RRCAT indoor. We have done with the curved hollow shafts, and this one propeller shafts also we have done. It's possible. Since it is pulsed laser, it is possible. And you can search in website also, laser shock peening. You can get a lot of videos. In India, it is developing actually, but in foreign countries, a lot of advanced techniques are there. Nowadays, people are using this type of technique for peening itself, like it is not laser ablation or laser ablating, or this kind of peening operation is used in additive manufacturing itself. Along with the additive manufacturing process, people are using this kind of lasers to peen or to finish the surface. Cladding, you might have heard of cladding and all, laser cladding.